So in the last set of lectures, we talked about Ampere's law. We introduced it. And so now what I'm going to do is just go through one more step-by-step example of how to approach Ampere's law. This is an example that we already saw, but I thought it'd be worthwhile just to kind of go through it again step by step. So basically we have this relationship, Ampere's law, which says that the integral of the magnetic field around some closed loop is going to be equal to this constant mu naught times the net current enclosed in that loop. Now, Ampere's law is very analogous to Gauss's law for calculating electric fields. So it turns out that this relationship is always true, but it only actually helps us solve for the magnetic field in specific circumstances. So if you're encountering some problem, the first thing to do is to figure out whether or not the symmetry of the problem actually allows for sort of employing Ampere's law to get your magnetic field easily. Okay, so that's the first thing to do. We're going to now consider a case that we've already seen. It's the infinite sheet of current. So it's infinite sort of in this lateral dimension here. It's sort of very thin, so we're not going to worry about its width. And then it's carrying a current out towards you, so out of the screen in the z direction. Okay, and so by symmetry, right, we know that if this is infinite, right, the magnetic field can really only be pointing in sort of in one of two ways. So either it's pointing straight out of the page, or it's pointing sort of horizontally, right? So if we use our right-hand rule, and we've already encountered this problem in one of the problem sets using the Biot-Savart law, if I stick, I consider the magnetic field from one of these little wires here that comprises the sheet, and I see it'll generate a current this way, right? So I can kind of convince myself it's not going to be a vertical field, it's going to be a horizontal field. So the field should look something, that's not very horizontal, but the field should look something like this, right? It should be kind of just going exactly sort of parallel to the sheet. Using the right-hand rule, I can convince myself it's going to the left above the sheet and to the right when I'm below the sheet. Okay, I'm not going to make any assumption about how the magnetic field is varying as a function of height above the sheet, but I can sort of convince myself, okay, it should be doing something like this. All right, so that's step one. So step two is basically we need to think about how many different regions of space we need to consider in this problem. Actually, so this is actually going to be written out in, I'm going to attach a sort of a handout at the back of this set of lecture notes. But, sort of determine how many regions of space we need to consider. In this case, we're going to think of the sheet as being infinitely thin. So basically, there's the space above the sheet, the space below the sheet. When we consider our Amperian loop, we can actually sort of, draw a loop that spans both these spaces. However, if this sheet was not infinite, like very, very thin, like let's imagine it had some kind of thickness, okay? So instead of sort of this, linear charge density here, this current density, we basically have this is an areal current density. We basically have a volume current density, right? So imagine it was like this thing was not an infinitely thin sheet, but a slab, infinitely wide slab. Then there would be some regions like where we'd have to calculate the field inside the slab, right? And the amount of current enclosed is going to sort of depend on how big my Amperian loop is. It's going, depending on how tall it is, it's going to enclose more and more current. So in this problem, we wouldn't have to worry about it, but in another problem, we might if, for instance, we have to integrate over some kind of current density, okay? In this case, basically, because this is very thin, we're not going to have to worry about that. So For step 3, we want to now construct our Amperian loop. And we want to construct it in a way that basically allows us to easily calculate this line integral. Right? So basically, instead of, I could make an Amperian loop, like a circle, right? But that wouldn't be a very smart Amperian loop because, if I look, basically, my line integral is going to be along the circle, the direction of dl, which is the circle, and the magnetic field is going to be changing, right? B dot dl is going to be changing continuously around the circle. So that would sort of be a bad idea. It wouldn't, it would be kind of a difficult thing to evaluate. So we wouldn't choose that as our Amperian loop. Okay? So what we would do instead is we would pick an Amperian loop where evaluating this is very easy, which means we want basically to make some kind of closed loop where B is going to be either sort of constant and parallel to a side of the loop, of our loop, or it could be, for instance, 0, or it could be perpendicular, right? If B and dl were perpendicular, the contribution to that part of the integral is 0. So it's very much like when we were constructing Gaussian surfaces, we wanted sort of, sides of the Gaussian surface where the electric field was either punching out exactly perpendicular, or it was sort of parallel to the Gaussian surface, so the contribution was 0. Same strategy for the Amperian loop. Okay, so let's imagine that this might not be a bad Amperian loop, right? Because since the field lines are parallel, it might be good to draw a square loop where the sides are either exactly parallel or exactly perpendicular to the field lines. And that's why we drew the field lines first, right? And I'm going to choose my direction of my loop. So I'll choose it like this, such that the direction of B and dl are sort of parallel, okay? All right. So I've constructed my Amperian loop, and I've done so in a fashion that makes it very easy to evaluate this integral, right? So step 4 is basically to evaluate B dot dl. So we'll call this side 1, side 2, side 3, and side 4. So basically, if I integrate B dot dl, it's just the integral along side 1 of B dot dl, plus. So we've got all these components here. So first of all, we notice that side 2, for instance, is exactly, B is going exactly to the left or to the right. Side 2 is going straight down. So basically that contribution to the integral is 0, and same with side, I kind of numbered this in a funny way, didn't I? It doesn't really matter. So side 3 is also 0, because the field lines are exactly perpendicular to the path. So only side 1 and side 4, the top and the bottom, contribute. And since the magnetic field is going to be, it's not going to be varying laterally, because it's a uniform sheet, it's just going to be B, and we'll call this, so we'll say this top surface has some length L. So B dot dl is just going to be equal to, for the top sheet, whatever B was. So let's say we wanted to calculate the magnetic field at this point here. It would be, whatever B is, and we're going to solve for that, times L. So that's from side 1. And then you can also see from side 4, assume that side 1 and side 4 are basically, let's say, equidistant from the sheet, right? Because, we don't want to assume that B is not changing as a function of height, although when you did the problem, solved it using the Biot-Savart law, that's what you found. But, we don't want to assume that. But if we assume that, but if we say that, side 1 is sort of, some height h above the sheet, and side 4 is the same distance away, then I think it's pretty easy to convince yourself that the magnitude of the field, just by symmetry, the magnitude of the field on top should be the same as the magnitude of the field on the bottom, just pointing in the opposite direction. Okay, so basically, from side 4, it would be the same B. B is reverse direction, but so has DL. So that's so basically those add. Okay, there's no negative sign there because basically in both cases B and DL are parallel. Okay, so that gives us, so that's step 4. We've evaluated B dot DL, and we got 2 times B times the length of our Amperian loop. So that's quite easy because we picked a good Amperian loop to use. If we picked a circle again, that would be really hard to evaluate. So step 5 is to evaluate the right side of the equation. So we evaluate mu naught I enclosed. So over here now, to get mu naught I enclosed, right, basically we know that the current density here is J naught coming out of the screen. To get the total current, we're going to have to multiply that by, this is, so we'll say this, in this case, because it's an infinitely thin sheet, we'll say that basically this current density is going to be basically a current per unit length. So it'll just be J naught. So it'll be mu naught times J naught times the length of this. If it was a slab, then it would be J naught times like the area enclosed, okay? But we're saying this is an infinite sheet, a thin sheet. So J naught times the length, right? So the longer the loop, the more of these little wires, if you will, are enclosed, so the more current's in there. Times L. Okay, so now what we have is we can equate these two things, right? So we know these two quantities are equal. So we have 2BL is equal to mu naught J naught times L. So we're going to find that the L's cancel, which is good because the magnetic field should not depend on the length of some arbitrary Amperian loop that we've constructed. So then basically B, right, the magnitude of B is going to be equal to mu naught J naught over 2. Okay, so for the top surface, I want to make this a vector. We can see it's pointing to the minus x direction, so that would be a minus I hat. And then for the bottom, the way we've defined our coordinate axes, it's going to be now in the plus x direction. So plus I hat to plus I hat. You'll encounter, an example where this sheet has some finite thickness. So then you have to kind of consider how many regions of space, right? So you want to consider then if I have an Amperian loop that sort of completely, pierces through the slab, or I could make a small one, right, that kind of lives only inside the slab. And here, for this one here, the amount of current enclosed will depend on how thick, how tall this little loop I pick. You'll see that a little bit later. I have a chance to work through that. Okay, so a couple caveats I want to mention about using Amperes' law. And that is that, again, much like in the case of Gauss's law, if, for many problems, the magnetic field lines will not be symmetric enough to allow you to really easily evaluate this line integral, right? So again, like in Gauss's law, the real trick to using Amperes' law is picking if you have the right symmetry or the right kind of configuration, is picking your loop, or picking your Gaussian surface for an electric field, such that I can basically write my line integral uh, as basically the magnetic field times some length, right? In the case of Gauss's law, it would be I could basically pull the electric field out of the integral and multiply the electric field by some surface area. The same goes with the Amperian, with your choosing the right Amperian loop. But again, you have to make sure that the situation is suitable for doing that, right? So for instance, if I have, again, so we have the example of, so when to use Ampere's law. So if your problem has a perfect cylindrical symmetry, and so that means you have an infinite wire, infinite thin wire, infinite cylinder where the current density is not changing azimuthally. Right? So for instance, if we had something like an infinite wire, or infinite wire coming out towards us, we know the magnetic field is going to be exactly circular. So what that means is, I can pick my Amperian loop to be corresponding circles. If my wire was infinite, but let's say it wasn't circular, I don't know, let's say it had some kind of like square cross section, okay? Then the magnetic field is not going to be exactly circular, right around, right around the wire. It's not going to be perfectly square either. So it's going to have some kind of somewhat, not exactly symmetric shape. It'll be fourfold symmetric, but it won't have perfect circular symmetry. It won't be a perfect square either. So basically, what you would find then is because of this, it would be very hard to define a, the right Amperian loop, where you can just say, well, B is either exactly parallel or perpendicular, because here it's going to be sort of curving a little bit. So this is not, so a square wire would not, square cross-section wire would not allow us to use Ampere's law. Okay, so we want perfect cylindrical symmetry. We have, again, the infinite sheet of current that I just talked about above. And then another thing we'll encounter is an infinite solenoid. And one sort of special case for that is a toroidal solenoid. Not going to be able to spell this. I think it's probably right. Where sort of the front, the front of the solenoid and the back of the solenoid are connected, right? So it's like a donut. So we've encountered the infinite sheet of current, and this could be a thin or a thick sheet. But it could not be a sheet where the current is varying laterally. So if there was like more current on this side than that side, that would sort of ruin the symmetry of the problem, because the magnetic field, for instance, might be stronger over here than over there. And so we can't assume that the magnetic field is exactly constant along this side of our Amperian loop, right? If we had more current here than over there, then the magnetic field here might be stronger than there, and then that makes it really hard to evaluate that integral correctly. Again, when you're trying to figure out when you can and can't use Ampere's law, well, there's, and I guess the fourth condition is sort of any combination. So same as in Gauss's law, right? If you have, an infinite sheet plus an infinite wire, you can just use Gauss's law for an infinite sheet by itself, the infinite wire by itself, and then the total field is just the superposition of those two. So any combination of, you know, the above situations. So what I want to do now is to spend the last part of this video talking about magnetic materials. So this is a little bit of a change of pace. But, when we first introduced magnetism, right, and magnetic forces, we basically said, oh, we were using like bar magnets, right? I would take out a bar magnet, and I would bring a wire close to it. So that bar magnet is generating a magnetic field. We've been talking about moving charges, like currents. So this is some kind of flowing charges as generating magnetic fields. But apparently, if we have a bar magnet, that thing also generates a magnetic field, right? So there are actually materials, and that bar magnet is called a ferromagnet. So there's actually various classes of magnetic materials. Some of them are analogous to dielectrics. So when we learned about electric fields and like capacitors, we said, oh, we can increase the capacitance of a capacitor by shoving this material called a dielectric in between our parallel plate capacitor. And so much like you have these dielectric materials for electrostatics, we also have magnetic materials. So we have a bunch of different classes of materials. And those basically fall into three categories. The categories are diamagnets, or diamagnetic materials. We have paramagnetic materials. And we have ferromagnetic materials. Okay, ferromagnetic materials are basically like your bar magnet. Actually, the theory for whether a material is diamagnetic, paramagnetic, or ferromagnetic is actually very interesting. It involves a lot of quantum mechanics. So for those of you that are studying, chemistry or material science, you'll learn about quantum mechanics. You'll learn about the atomic shell structure of materials. So it turns out that the orbitals, right? You learn about s, p, d orbitals. Those orbitals have different amounts of orbital angular momentum, as we call it, and also depending on the occupancy of the electrons in those orbitals, there are basically spin moments. So basically, as you probably have heard, electrons have spin, and those spins act like little bar magnets. So depending on the occupancy of the orbitals and which orbitals are themselves are occupied in the number of sort of what we call uncompensated spins in them, that basically determines whether materials are diamagnetic, paramagnetic, and ferromagnetic. And so it's actually very interesting. And even today, our best theoretical calculations oftentimes have trouble determining whether materials might be ferromagnetic. So you can do very complicated quantum mechanical calculations, but in reality, actually, ferromagnetism comes from interactions between electrons. And those are actually notoriously hard to calculate. So we can sort of guess, why, for instance, materials like iron and, cobalt are ferromagnetic. But actually, we don't have an exact theory to describe these behaviors. We basically have sort of approximate theories that treat the electron interactions in an approximate way. I mean, this is all a little bit above your pay grade for this class, but it's very interesting if you want to know more about it. I mean, I'm sure you can, if you Google, about Google ferromagnets, I'm sure there'll be lots of information that you can look through. But it is actually a very active field of research right now. It's something that, for instance, personally, I'm very interested in, is trying to find materials that are even stronger ferromagnets, or, for instance, may exhibit very strong ferromagnetism at high temperatures and things like that. But back to 2213. So a diamagnetic material is one. So imagine I have a chunk of material here. Okay. And I'm going to, there's a magnetic field. B naught, an external magnetic field that's been applied. And a diamagnetic material will respond to that magnetic field by having the magnetic dipoles inside align in such a way. The magnetic dipoles in the diamagnetic material will align in such a way so that they will generate a field inside that will basically partially, actually, and by partially I mean actually to quite a weak extent, try to oppose the applied magnetic field. Okay? And generally diamagnetism is generally, for most materials, quite weak. Okay? So this, so the case of the diamagnetic materials is very much like what we had in the dielectric materials, right? So if you remember, in dielectric materials, when I applied an electric field, let's say upwards, there was basically an accumulation of positive charge on the top surface and an accumulation of negative charge on the bottom surface, which basically meant that there would be an electric field generated by those surface charges that would oppose the applied electric field. So what that means then is the net field inside this little slab of material is going to be weaker than the applied field outside. Okay? Then we have the opposite case, which is basically a paramagnetic material. And in a paramagnetic material, basically what you find is that the magnetic moments will align with the applied field. Okay, and so opposite to the case of diamagnetic materials, the field inside the paramagnetic material will be a little bit stronger because basically these two fields are adding together. All right. And then finally we have a ferromagnetic material. A ferromagnetic material is quite interesting because in the case of a diamagnetic material and a paramagnetic material, what you find is that as soon as you remove the external magnetic field, there is no magnetic moment, or there is no magnetization, if you will, left in the diamagnetic or paramagnetic material. So that this green arrow here only exists when you apply an external field. Okay, but when you take that field away, these green arrows go to zero. These things basically have no basically net magnetic behavior. A ferromagnet is quite different, as you know. That basically has a magnetic moment even when you have no magnetic field applied. Okay, and the reason for that is that there are electron spins. So if you look at, for instance, at a chunk of iron and you look at the iron atoms have a net spin, and the spins on the different iron atoms are interacting in such a way to cause them to align. Okay, and actually ferromagnets are quite interesting because if you heat them up to high temperatures, the magnetism goes away, and so as you cool down below what's called the Curie temperature, the electron spins inside undergo a phase transition. And it turns out that phase transition is very similar to the phase transition that happens when you are condensing water or boiling water. Okay, so that, as you know, is a phase transition between the solid and gas phase. There's a phase transition that happens on the electron spins that when they go from basically being pointing in all sorts of different directions to pointing all in similar directions. That is a phase transition that happens when you cool the material down below some given temperature. For iron, it's lucky for us that that temperature is quite high. It's well above room temperature. It's many hundreds of degrees. So that means these materials act ferromagnetic at room temperature. There's many materials that only become ferromagnetic when you cool them down very close to absolute zero as well. So this is and that temperature again is called the Curie temperature. Okay, so I'm going to talk first about diamagnetic and paramagnetic materials. So as I said here, if I think about the total magnetic field inside the paramagnet or the diamagnet, it's going to be equal to B naught, the applied field, plus I'll call this Bm, that's basically the field generated by the magnetic material itself. So that's the green field, okay? So basically our treatment of diamagnets and paramagnets is very, very similar to what we did for dielectrics, okay? And exactly like the case for dielectrics, we found that this the field generated by the dielectric was basically proportional to the external magnetic field applied. The stronger that you apply the field, the sort of bigger the green arrow. Okay, so for diamagnetic materials, the larger the external magnetic field, the more strongly the material tries to fight that magnetic field. With paramagnetic materials, the stronger the external field, the more the magnetic material tries to help that magnetic field. Okay, so there's a proportionality constant, which we call chi. So it's not, let me try to do that again. Geez. Chi sub m. Okay, so it's not an x, it's chi. B naught. So it's supposed to be proportional to the applied magnetic field. So this basically represents basically B sub m. That's basically the magnetic field generated by the diamagnet or the paramagnet. So I can also just write this. If I factor out B naught, I can just write this as 1 plus chi sub m. Okay? And chi sub m is we call this the magnetic susceptibility. And then there's another quantity, which is basically 1 plus chi sub m, which we call kappa sub m. And that is the magnetic permeability. Okay, it's a little confusing. I'm not sure why we decided to have two different quantities that basically tell you the same thing. I probably spelled this wrong. But yeah, so basically chi sub m is basically sort of, you can think of this how much extra the diamagnetic material, the paramagnetic material is helping or hurt, or fighting the external field. So it's sort of that little extra bit. Chi sub m is sort of the entire behavior of the applied field plus the sort of helping or fighting of the diamagnetic or paramagnetic material. So this whole thing is kappa sub m. So for diamagnetic materials, kappa sub m is going to be less than 0, or in other words, kappa of m should be less than 1. And for paramagnetic materials, chi sub m is greater than 0. Kappa sub m is going to be greater than 1. So actually, I just had to correct something here. Actually, kappa sub m, I got this backwards. Kappa sub m is called the relative permeability. The magnetic permeability is when you multiply kappa sub m by mu naught. Okay, there's a lot of terms, different terms here that basically are all saying the same thing. Personally, I prefer chi sub m, the magnetic susceptibility, because it's sort of, to me, the most physically significant quantity. Okay, so one thing to remember, to actually keep in mind is actually, when I mentioned a couple times that the magnetic forces are in general much weaker than electric forces. And so when you learned about dielectric materials, we found that actually, the dielectric constants of certain materials can be very large, right? They can be sort of tens or hundreds. And so we can really dramatically, increase the capacitance of capacitors by shoving in, some dielectric goo in between the plates, right? Some kind of plastic or something like that. The magnetic susceptibilities are, in fact, very small in general, okay? So chi sub m, in general, for diamagnetic and paramagnetic materials, chi sub m, the absolute value, whether it's positive or negative, is typically on the order of about 10 to the minus, we'll say 10 to the minus 4 to 10 to the minus 6, okay? So basically, if you apply a magnetic field, the enhancement for a paramagnetic material, or sort of how much it's reduced in a diamagnetic material, is something on the order of, it's less than 1 part in 1,000. So if I applied, a 1 Tesla magnetic field to a typical paramagnetic material, the field inside would be maybe like 1.00001 Teslas, or for a diamagnetic material, it might be that 1 Tesla field might get knocked down to a 0.9999 Tesla field. So it's generally a pretty small effect, okay? So chi sub m is pretty small for dia and paramagnets. And, for instance, all sorts of different kinds of metals can be either diamagnetic or paramagnetic, right? So for instance, a paramagnetic material, aluminum is paramagnetic, sodium, all sorts of materials. These are just some random ones, okay, platinum. Whereas, copper is diamagnetic, lead, silver. So, but generally, like I said, these effects are pretty weak, right? So if you're applying a magnetic field and you're doing it to a chunk of copper, if you're applying a 1 Tesla field, the field inside generated by, the diamagnetism of the copper will basically knock down the total field by, less than a part in 1,000. The ferromagnetic materials are sort of an exception. Okay, so ferromagnetic materials are one where basically you need a very, generally, oftentimes the magnetism is in domains, and you need a very, very weak field to align those domains. And it turns out it's oftentimes quite easy to scramble those domains. So, for instance, if you ever dropped a refrigerator magnet, you'll notice that actually sometimes it doesn't stick as well. The reason for that is because when you drop it, actually that the mechanical energy that's dissipated when you drop the magnet oftentimes can go into scrambling the domains. You can always reorient those domains by applying a larger magnetic field, which will reorient those moments. I just want to make one last definition. We have a lot of different quantities here. Don't worry, when it comes time for your prelim, we'll make sure that these are all on your equation sheet. There's another quantity m here, okay, which we call the magnetization. And again, like these other quantities, it pretty much is just another way of expressing chi. So the magnetization of the material can be written as follows. So B total is equal to B naught plus mu naught times M, right? So basically that mu naught times M was our B sub M. That was basically the magnetic field that was generated in the diamagnetic and paramagnetic materials. Okay, so that's it for today, and we'll talk a little bit more about these magnetic materials in lecture.